This is session number 6 of fluid mechanics. And we are into the final part of this, which is hydrodynamics. So as we discussed, as part of hydrodynamics, we will be studying one particular type of motion of fluids, and that is classified or defined as the steady flow, or also called streamline motion or streamlined flow of an ideal fluid. So what happens in the case of streamlined flow of an ideal fluid is that if this is a pipeline or a passage through which fluid is flowing in such a way that the fluid elements or volume elements of fluid, just visualize small differential mass elements or volume elements of fluid, as they are moving, they move along clearly defined trajectories or paths, which we call streamlines. And these clearly defined trajectories or paths are fixed with respect to time. That means one fluid element that is moving like this at one point of time, having a velocity like this. Now, the moment that passes this position and some other fluid element comes and occupies this position, it'll have the same velocity vector as the one previously. So basically, the fluid elements are following each other in a well-defined and well-ordered kind of motion, in which their trajectories are along fixed paths. Okay, so that is called the streamline motion. So streamline motion or steady flow involves the what we defined as the irrotational and non-turbulent. So there aren't any violent collisions that are suddenly and randomly occurring to create turbulence or sudden changes in pressure. So that is non-turbulent motion of fluid elements. So what we mean by fluid elements as volume or mass elements of the fluid. So it involves the irrotational and non-turbulent motion of such fluid elements such that they move along well-defined and steady trajectories or paths. And these are collectively called streamlines. Okay, so this was the initial groundwork that we had done in the previous lecture related to steady flow or streamline motion. Okay. Towards the end, that is. Okay. Now today we will continue with the mathematical analysis of this type of motion further. Okay. So we had also seen the properties of the streamlines, that wherever the streamlines are more closely packed together, that is, the number of streamlines per unit area of cross section is larger, there the speed of flow or the velocity flow of flow's magnitude becomes more. And wherever they are a little bit further apart, because the area of cross section is wider, the speed of flow or the magnitude of velocity of flow becomes lesser. So that was the additional thing. And of course, at any point, the direction of the velocity vector is along the tangent to the streamline passing through that point. So these are two additional definitions we had seen. Now, the next aspect that we will look at is that in streamline motion, at a particular cross section through which streamline motion is happening, or through which fluid molecules are passing in streamline motion, at a particular cross section, the velocity of flow is a fixed quantity. That means all fluid elements passing through a particular section will have uniform velocity. Okay. And that uniform velocity remains constant with respect to time for every fluid element passing through that section. So what we mean to say is that if we consider a cross-sectional area of the pipe like this, okay, so this is not a separate object. We are just imagining a cross-section of the pipe at a certain position. Then every fluid element or every fluid particle, you can say, passing through that cross-section will have the same velocity. So at any instant of time, if you compare two fluid elements that are crossing that cross-sectional area, that are going across that cross-sectional area, they will have identical velocity. And also, if you see one fluid element passing through that cross-section just now, and a little while later, another fluid element that was behind it follows its path and goes through that cross-section. So the one that followed its path will also have the same velocity as it went through that section. And the next one following it will have the same. So the velocity of every particle going through the cross-section is not only same at a given instant of time, but also through time. Any fluid particle or any fluid element going through that particular cross-section will have a fixed velocity. So that's another important property of the streamline motion. So the velocity of flow for fluid elements through a particular cross section, okay, remains uniform for all fluid elements at the given cross section and at all instants of time, or you can say at any arbitrarily chosen instant of time. Okay. So what that basically means to say is that if we are looking at this particular cross section right now at a time t1, so we notice that there are fluid elements passing through it. They are moving with the same velocity v. Now, if we look at that same cross section a little while later at t2, again the fluid elements which are present here will again have the same velocity as the previous ones. So that is the meaning of saying that they are constant with respect to time, and they are constant with this, and they are uniform with respect to the entire cross section. So this is again an important theoretical consideration to understand before we start coming into the maths equations that describe the steady or streamlined motion. Oh, actually, we have noted down this point earlier also. So we have noted down all the properties of streamlined motion, including this point in the previous lecture. Anyhow, so we'll just recap through these points.
Sir,
Yes.
sir, can you show the first page?
Okay, so this section is there in your previous lectures class notes also. So you don't need to write this down again. Just need to make sure you understand this point, because now we are coming to the maths equations where we'll be using this. Okay. So Samarth, yes, to come to your point which you asked in the text message, velocity of all particles particles at a particular cross section at a given instant of time will be same, will be equal. But at a later instant of time, when there's a new set of particles at that same cross section, even they will have the same velocity. That means at a particular cross section, we have a fixed amount of velocity. Any and every fluid element or fluid particle passing through that cross section at any point of time will always pass through with the same constant velocity. Hope that point is clear now. Runner can sum up both. Okay. So as I said, you don't really need to note down these points. These are already there in your previous lectures. Lecture 5 towards the end, when we are discussing the basics of the definition of streamline motion, we had gone through all these points. Okay. Now let's come to the maths equation parts of this. So equations related to streamline motion. This is what we'll be using in solving problems. Okay. Equations for streamline motion or steady flow. Obviously for an ideal fluid. So there are namely two equations. One is, the first is called the continuity equation or equation of continuity, which is basically like an expression of the fact that the liquid is incompressible, that is, its density remains uniform. But it's a logical way of expressing that in terms of the motion parameters, that is the speed of flow and the cross-sectional area through which the fluid is passing through at a given cross-section. So let's understand that one. So this is called the continuity equation or equation of continuity. So to understand the continuity equation, just consider a section of a pipe through which fluid is in streamline motion. Now consider a section of the pipe between this cross-sectional here, which is of area A1, let's say, and the fluid is flowing through with a velocity V1. And just select arbitrarily any other cross-section A2, where the liquid is flowing through with a velocity V2. Now consider this section of the pipe in between. So I'm just shading it out. So if you consider this
Sir, it's
section
a
of the pipe,
uniform pipe. Sir, it's a uniform pipe.
no, obviously not, because I've taken A1 and A2 different. It's not a uniform pipe. In general, it will never.
Okay, so the velocity will differ.
So the velocity will differ. So the important thing is continuity equation will tell us the relationship between V1 and V2 and how it will express that relationship by going back to the fundamental property of the streamline motion and the fact that it's an ideal fluid, that liquid molecules are moving in pure translation through this section because it's irrotational motion, and they are moving in such a way that there is no turbulence. So there's no sudden change in pressure because of collisions and all that. So that means the density of the liquid in between these cross sections should be constant. So if the density is constant, that means for this fixed section of the pipe, the total volume of liquid at any instant of time should be constant. The total volume, or you can even say the total mass, or the total amount of substance, in that sense, you can say, should remain uniform. So what is happening is, if you just consider the section of the pipe between A1 and A2, liquid is pouring in through the cross section A1 at a certain rate, and liquid is pouring out through the cross section A2 at a certain rate. Now, in some time delta t, the amount of substance that comes in from one section should be equal to the amount of substance that goes out from the other section. Okay? So continuity equation will just express this, that so considering a fixed section between two cross sections of area A1 and A2, in time delta t, the volume of fluid entering the section will be equal to A1 into V1 delta t. I'll explain why this happens. Okay. And the volume of fluid exiting the section will be equal to A2 V2 delta T. Okay. Now, the total volume within this section must remain constant. So therefore, the volume entering must be equal to the volume going out. So A1 V1 delta T must be equal to A2 V2 delta T for any length of time. So delta T can be a very short time dt. It can be a relatively long period of time also. But whatever be the case, the total volume coming in should be equal to the total volume of liquid going out. So in general, we can say that A1 V1 at any point is equal to A2 V2 at any other point. Now, since we can select these two cross sections arbitrarily at any 2 points within the fluid, so therefore, in general, we can say that the product of area into velocity should be constant. But by velocity here, I mean speed actually. It's the magnitude of velocity. I'm not writing a vector equation. So it's more like we in everyday language, we use the term flow velocity, but what we actually mean is the magnitude of flow velocity. So in general, area of cross section into speed of flow at any point is constant in a streamline motion. Okay. Now let's understand why this term is there, A1 V1 delta T. Okay, so for that, we'll come back to this for you to write down. But now just let's look at a somewhat magnified diagram. So now let's say this is the cross section where the area of cross section is A1 and the liquid is flowing through this cross section at a velocity V1. So in a time delta T, in a relatively short amount of time delta T, the volume of liquid that enters through here will be the volume of this section. So if this section is, let's say, a ds, okay, so the volume of liquid that is entering through that is area into that cross section ds. Okay, but if that time, so this is the volume dv that passes through in time dt. Okay. Now, since this is moving at a speed v1, so basically ds will be equal to v1 into dt, because all these fluid particles here are moving at a constant velocity of v1, the uniform velocity v1 through the cross section. So that means the volume passing through in time dt, which is a1 into ds, is equal to a1 v1 dt. So in other words, we can say that the volume passing through in a certain time delta t is just a1 into v1 is a constant. So it is nothing but a1 into v1 into the amount of time delta t, whether that's a short duration of time like dt or it's a longer duration of time. So this is the logic of how we can understand that at a cross section of area A, if the speed of flow is v, then the volume of liquid passing through that cross section in a time delta t will be product of area into velocity of flow into time delta t. Okay, so this final equation that we've got over here, this is called the equation of continuity. Whether we write it in this form or this form, it's one and the same thing. This is called the equation of continuity or continuity equation, whatever we choose to call it. Okay, so make a note of this quickly. Okay, so now one more thing we'll understand about this continuity equation is that the quantity area into velocity is actually volume flow rate. That is volume per unit time flowing through a cross section. This implies basically that the meaning of the statement of continuity equation implies that the volume flow rate that is a product of area of cross section into speed at any of the cross sections is uniform, and it has to be uniform because of the nature of streamline motion, that the liquid is incompressible and the motion is steady, or it is non-turbulent and irrotational. So also from this equation you can see that dv at a point is area into velocity into dt. So volume flow rate dv by dt is A into B. Now this also supports something that we have understood from the visual diagram of streamlines, something that we have written earlier, that at a point where the cross-sectional area is less, so the density of field lines is more, the volume flow rate will, the velocity of flow will be more, because product of A into V is constant. So wherever area is less, V has to compensate by being larger, and wherever area is larger, so the density of the streamlines is less. They are less densely packed. There, the velocity of flow has to be larger in bracket. Okay. So A1 V1 equal to A2 V2 means that, as you can see in the diagram, wherever the area is smaller, the velocity of flow is larger, and wherever the area is larger, the velocity of flow is smaller. So large area also means less density of field lines. So less density of streamlines means less magnitude of velocity. More density of streamlines, that means the cross-sectional area is lesser. So there the speed of flow is greater. So something that we had understood qualitatively earlier while analyzing the construction of the streamlines, now we understand it exactly in the mathematical equation, that product of area into speed of flow is constant. So let us see some of the implications of this. So for example, if we consider the most, you can say, trivial case of steady flow, that is, we have a horizontal pipeline of uniform cross section. So steady flow through a horizontal pipe of uniform cross section everywhere. So this is the simplest case that we can think of. Gravity is not playing a role because the fluid is flowing through a horizontal pipe and the cross section is uniform. So it is the most, you can say, simple and ordered kind of motion, because literally it is a uniform 1D motion for fluid elements. So we visualize fluid passing through this kind of a situation. Okay, so let's say the pipe is indefinitely long. We are just drawing a certain section of it in our diagram. So within that section, if we consider any two positions where the area of cross section here is also equal to some A, and at any other position also, the area of cross section will be E. So that means whatever is the speed of flow through this section, suppose that's V, the speed of flow through this section will also be V. So now the more important thing is, if you consider a fluid element that is flowing through, okay, this thing, they're all flowing at constant speed like this. So if you consider a fluid element that is a differential mass or a differential volume of fluid going from section 1 to section B. So as it is going in what type of motion? A fluid element flows in uniform 1D motion. So its acceleration should be 0. So if its acceleration is 0, that means the net force acting on it must be 0. So if you think of the free body diagram of that fluid element, okay, if the pressure from this side is P and the cross-sectional area is S, okay, then the pressure from this side must also be the same and the cross-sectional area, because its acceleration is 0. So net force must be 0. Okay. So if this is a fluid element of cross-sectional area S and length delta L, so its volume is S into delta L, its mass is density into cross-sectional area into delta L. So that kind of a mass it is. Okay. Now because its acceleration is same, the pressure is 0. The pressure must be uniform from both sides. Okay. Because of this, because the net force must be 0. So this implies that pressure must be uniform, okay, on both sides of any such element. So that means now if we consider any 2 points within the fluid, like the point over here. So if we consider the pressure at this point as P1 and the pressure at this point as P2. So this also tells us that P1 must be equal to P2, or pressure at all points inside fluid in the above case must be uniform. Okay. So that is the only way, as a fluid element is going across any section of the pipe from one point to another at this uniform velocity, it should not experience any net force at any point of time. So that means at any point of time of its motion, the pressure on both faces of that fluid element, the pressure must be uniform. So continuity equation here is not only giving us information about the speed of flow is uniform, okay, that is V1 is equal to V2 in this case, but it's also giving us extra information that the pressure throughout the liquid in this situation where it's flowing horizontally through a uniform cross section pipe, the pressure must be uniform. Okay, so additionally it is giving us this information also, that in the case of steady flow through a horizontal pipe of uniform cross section, the speed of flow is uniform. So firstly, we have A1 V1 is equal to A2 V2. So since A1 is equal to A2, okay, therefore V1 must be equal to V2. So this is the first thing that we are seeing, that the velocity of flow V is uniform at all points. And then when we apply that concept of uniform velocity for a fluid element that is going through like this, we also understand that additionally pressure is also uniform at all points. So make a note of this trivial example of application of continuity equation, which is telling us not only about velocity of flow, but it's also giving us some information about pressure. No, Dhruv, acceleration can be non-zero in a horizontal pipe also. I'll explain the next example in which that will become clear. But in this case, the acceleration will be 0, because not only it's a horizontal pipe, but the cross-sectional area is uniform. So both the conditions are equally important, horizontal and uniform cross-section. Okay, now let's look at the next situation of Aditya. You didn't copy a few lines. Okay, I'll just scroll up. So this is the section about the continuity equation which we had discussed just before the application of this.
Yes, sir. Okay. Thank you.
Okay. So then this example you understood, na, Aditya?
Yes, sir. Understood.
Okay. Now next let's look at a situation where something like this is happening. We still have the horizontal pipe, but it's not of cross section uniform. It's, let's say, tapering like this. It's slightly tapering, not that it's like, not like a very sharp change in area like a cone or something, but it's slightly tapering. So the area changes from position to position. So in this kind of a situation, so in this now, if there is a fluid which is flowing in streamline motion, so if we draw the streamlines quite accurately, then we'll already be able to understand that the density with which the streamlines are packed doesn't matter what is the direction of velocity, left to right or right to left, but the density of packing of the streamlines is lesser over here in this section where the area is more. So let's say this area is A1, and in comparison to that, this area is now quite a bit less. So if A1 is greater than A2, then even visually you can understand that V1 should be less than V2 because the lines are much closer at A2 and they are much further apart at A1. But what is the exact equation over here which will show us this relationship that A1 V1 will be equal to A2 V2? So since A1 is greater than A2, it will immediately show us that V2 is greater than V1. So in this kind of situation where we have a horizontal pipe but of non-uniform cross section, we will see that the speed of flow is non-uniform, which means that there is some kind of acceleration involved. Okay. So now when I consider a small fluid element as it's making a journey from this side to this side, it is undergoing an accelerated motion. Or suppose the flow velocity element would be undergoing a decelerated motion. So when you consider this fluid element, it's going in a direction in which its velocity is increasing. So it should have an accelerated motion. So a fluid element will have accelerated motion. So the moment you understand that it will have accelerated motion, you realize that the forces should not balance. So if the pressure from this side is P1, the pressure from the other side P2 should be less now, so that the acceleration is towards the right. So since it's accelerated, that means net force should not be zero. So that means P1 in this case should be greater than P2. Okay. So there is a pressure gradient. That means there's a pressure variation or variable pressure inside the fluid. Okay. And in general, if this region has pressure P1 and this region has pressure P2, as we go from left to right, the pressure should be decreasing. Okay. So this is such that, as we've already written above, P1 is greater than P2. This is the region, this is a cross section 1 and this is a cross section 2. So inside the fluid, as we move geometrically from the cross section 1 to the cross section 2, there should be a drop in pressure. The gradient should be in that kind of sense. So again, application of continuity equation is not only giving us an idea that the speed of flow is increasing as we go from left to right, but it's also telling us logically why the pressure should be decreasing as we go from left to right. Okay, now if we move this to a vertical situation, then things become a little more interesting because we have to take gravity into play. So next, let's understand a vertical pipe, but of uniform cross section. Now, sometimes our natural way of thinking that whenever there is motion in a vertical direction without any additional external force, okay, there should be acceleration due to gravity. But here you have to understand it is not motion of an independent object through gravity. It is motion of a continuation of particles, which are the fluid particles, which are all interacting with each other through pressure. Okay. So when you consider a volume element of fluid, which is in flow through this vertical pipe, it's not like that volume element is having zero net force acting on it other than gravity, because it's not like an object in free fall. That volume element is being influenced by the pressure at its various surfaces. Okay. So the correct way to analyze the motion over here will be first and foremost to understand that whether our fluid is flowing in the upward direction or downward direction, the relationship between the velocity of flow at any 2 points will come from the fundamental of continuity equation. So if this is a uniform cross section pipe, then if I consider any two sections, the areas must be equal. So therefore, if I consider the velocities, they must be equal. Okay. So as long as it's a uniform cross section pipe, we'll see that velocity of flow is uniform. Now you might ask that, okay, how come it's possible that against gravity over here, we are having a uniform velocity motion? It's happening because now if you consider a fluid element inside this, how it is undergoing unaccelerated motion is because there is different pressure acting on it from below and above. This is going up with a uniform velocity, so its acceleration is zero. So its acceleration is zero, that means the net force acting on it must be equal to zero. Okay. So that is only possible if the gravitational pull acting on that fluid element is balanced by, it is counterbalanced by the pressure difference, the force due to pressure difference. So the pressure from this side is P2, let's say. The pressure from this side has to be lesser so that these two together are able to counterbalance the weight of this element. That means P2 is greater than P1. So there is a pressure gradient or a pressure variation inside the pipe. Again, such that the pressure decreases with vertical displacement. Now you'll realize, obviously, if you think logically, that if we had a non-uniform cross-section pipe, like a tapering pipe, then this analysis would become more complicated because at two different points, the speed of flow would be non-uniform. Okay. So the motion of the fluid elements would be accelerated or could even be decelerated depending on which side has higher cross-section, which side has lower cross-section. And plus there's gravity to contend with. Sorry, come again. Any doubt, beta?
So just a second, we are copying.
Okay. Right, finished?
Sir,
Yes.
will P2 be always
Yes,
greater
sir.
than P1?
Hmm. Yeah, so that's what I'm saying, that P2 will be greater than P1 in this situation because the cross-sectional area is uniform. You know? So the fluid element is going up with zero acceleration, but then something has to counter gravity. But that's not always going to be the case. Now, we might have a situation like this where, for example, we have a tapering pipe like this. So here the velocity of flow is more, and here the velocity of flow is less if it's going the upward direction. So as something is going up like this, it's decelerating. So it could even happen that is decelerating because and is decelerating at a rate faster than gravity. So suppose that happens, that means the pressure from this side should be quite a bit more than the pressure from this side. Got it now?
Yes, sir.
So what we understand from these examples is that, see, so far we have not done any numerical analysis of the pressure. We've just understood that in certain situations, the pressure might be uniform. In certain situations, the pressure might have a gradient. But what are the situations dependent on? So they're dependent on, as we saw in the two horizontal cases, they're dependent on the speed of flow, whether the speed of flow is changing or it is remaining uniform. And in the vertical case, we've seen that is also depending on whether we are going against gravity or with gravity. So that means ultimately the pressure variation depends on both the factors, you know, how gravity is affecting the system in a non-horizontal situation and how the variable cross-sectional areas affecting the situation in terms of the speed of flow. So to put these things together and come up with a numerical analysis of how pressure varies, we have the second equation, which is applicable for steady flow, and that is called the Bernoulli's equation. The first equation was the continuity equation. The second one is Bernoulli's equation. Now, Bernoulli's equation is going to relate all these three things together. The effect of gravity, the effect of speed of flow, and the effect these two things have on the pressure at various different points inside the flow. Okay. So Bernoulli was the name of a physicist. So that's how this equation's name has come. Okay, so Bernoulli's equation is something that relates three parameters for streamline motion in a fluid. It is a relationship between pressure, say P, okay, flow velocity. But remember here by flow velocity, I just mean magnitude of the velocity. So it's more like flow speed, okay, and actually gravitational potential energy. Which we relate with in terms of the height h with respect to some reference horizontal level. So it relates these three parameters P, V, and H, where H is the height from some reference level for points inside an ideal fluid in steady flow. And it achieves this relationship by an application of work energy theorem. So we'll understand the derivation of it in just a moment. So it applies our good old work energy theorem from Newtonian mechanics. That work done by external forces plus non-conservative forces is equal to change in kinetic energy plus change in potential energy. That very theorem will be applying over here, but we'll be applying it to a section of a moving fluid instead of to a rigid body or to a particle. Okay? So by applying that, we will see that we'll establish a relationship between pressure, flow speed V, and the height of a given point inside the fluid with respect to some common reference level or some reference horizontal level. So we'll be relating these three parameters, P, V, and H. Let's see how we are going to do that next.
Sir,
Yes.
is there a graph to describe Bernoulli's equation after this?
We can make a graph between any two of the three parameters if one
Okay.
of them is constant. Understood? Because there are three
Okay,
parameters
okay.
which are changing. So
Okay.
typically, if all three are variable, now P, V, and H, then we have to make a
Yeah,
three-dimensional graph. So it becomes something that we can not do on pen and paper. But suppose we are talking about pressure variation with respect to speed for a horizontal pipe. So H is common everywhere. So then we can draw
Okay.
a graph. Okay?
Okay, okay. Yes.
So now you'll notice that as we do the derivation of Bernoulli's equation, all the properties of steady flow that we have discussed earlier, they will come into play. That's why it was very important to understand them in detail. Let's say this is some kind of arbitrary pipeline, which is neither vertical nor horizontal. It's kind of diagonal in orientation and does not have a uniform cross section. And through this, we have our fluid, which is as usual in steady flow or streamline motion. Now here we have also selected some kind of a reference horizontal level so that we can describe the height of different points with respect to that reference horizontal level. So this is our reference horizontal level. This is an ideal fluid of uniform density rho in steady flow. Now let's consider a section of this fluid bounded by these two cross sections. So let's just consider like a volume of fluid which is between these two boundaries at t equal to t. Okay, this is where the fluid section is located. And this cross section is moving at a speed v2 and this cross section is moving at a speed v1. And we know that a1 v1 is equal to a2 v2, which will be equal to the volume rate of flow. since it's a uniform volume rate of flow, we can also write it like an average volume rate of flow, delta V by delta T. Okay. Now this cross section, also over here the pressure is P1, and sorry, here the pressure is P2, and here the pressure is P1. The internal pressure at such a point is P1. Here the internal pressure is P2. Okay. Now, if we consider the same cross section, same volume of liquid, okay, which is bounded by these two, after a bit of time, after a very short interval of time, so this boundary has moved here, and this boundary has moved here. The whole liquid has shifted a bit like this. So this is at time t equal to t plus dt. Okay. So just drawing that in a little bit more detail. So this is how our section of fluid, a certain volume of fluid is looking like at the instant t equal to t. Now, with this boundary moving at speed v1, or rather v2, this moving at speed v1, this cross-sectional area a1, this cross-sectional area a2. But by the time an instant later we are looking at the same picture, a very short interval of time dt later, this boundary has moved, and also it has expanded a bit, of course, because the shape is changing. Something like this is happening. Okay, so this is how it's looking at t plus dt. Okay. So now you think of the free body diagram of this section of liquid as it is moving. What all forces are acting on it? So obviously there will be some contact force with the side walls of the container or side walls of the pipe, but those are like normal contact forces due to pressure. So they're not going to do any work. And there is no viscosity. So there's nothing like friction which is scraping against, creating dissipation of energy. But this cross section is being applied with a force because of the fluid pressure at this phase. So there's a certain amount of force, let's say F2, which is because of pressure. So that is pressure at that point into area. And similarly, this surface is being pushed downwards like this because of the fluid pressure from the fluid above this section. So that is F1 equal to P1 E1. So now as the fluid is moving in this sort of direction, you can see that this force F2 is doing negative work. This force F1 is doing positive work. Okay. So as this fluid element is moving from T equal to T to T plus dt, we can say that work energy theorem will tell us that the net work done by the external forces acting on it. Okay, there is no non-conservative force, so I won't consider that because there is no viscosity. That should be equal to the change in its kinetic energy plus the change in its potential energy. Or we can also write this like this, that we can write it in the language of delta. Okay, that work done by external force during a small time delta t is equal to the change in kinetic energy plus the change in gravitational potential energy. We can write it like this also, where this is work done by external forces. In this case, F1 and F2 that you can see in the diagram in time delta t. Okay. Or we can write this as dW, okay, the differential work done. Okay. That is the work done by these two forces in time dt instead of delta. Okay. And this is the change in kinetic energy in time dt. And this is the change in gravitational potential energy. In time, sorry, we'll write this as delta t because we are writing it as a delta k and a delta e. But instead of the delta notation, if we write it as a differential change in kinetic energy, then this will be time dt. Or if we write it as a differential change in potential energy, this will be time dt. Okay. So just note this down first. This is the general statement of work energy theorem. This or this. This is in differential form. This is in general form. So first of all, here we consider a section of the fluid. Let's say in the diagram, the section of the fluid is between the points M and N, this section. As it moves from time t to time t plus dt. So as that section of fluid is moving, okay, I'll just put aside the continuity equation for a moment because that's aside from this. Okay. So let's put that here. So this is not to do with the work energy application. This is to do with continuity equation. We have this result from continuity equation. But as that section is moving from time t to t plus dt or t plus delta t, whatever we choose it, okay, we can apply work energy theorem to it like this. That is, the work done by the external forces F1 and F2 that are acting on that section will be equal to the change in its kinetic energy plus the change in its gravitational potential energy. So just write it down up to this step, then we'll discuss further. F2 is the force acting on that cross section because of pressure. Okay. So remember, any surface inside a liquid experiences force normal to it because of pressure. So consider that section of fluid as it is moving, right? So on that face of it, which is facing down the pipe, there is a force acting up the pipe, no? Because it's acting normally into that face. Similarly, on the face of area A1, that face is pointing up the pipe. So the force acting on it is down the pipe. So that's why F1 is like this down the pipe and F2 is up the pipe. But they're both normal to the surface because they're pressure, force due to pressure.
So can you show previous slide also?
Yeah, Samar, to answer your question, no, whether the liquid is flowing up or down, if the cross section of the pipe is uniform, no, the continuity equation will tell us that the speed of flow is uniform. So that means it's a non-accelerated motion. Okay, so that means net force should be zero. So pressure at a lower point should be higher, pressure at a higher point should be lower. So same kind of pressure gradient will come. The difference will occur if the cross-sectional area is not uniform, because then the motion of the fluid elements is not uniform motion, it is accelerated or decelerated motion. Anyway, so Bernoulli's equation will finally give us the answer to not only understand how the pressure varies, but the numerical formula for that variation of pressure also. Okay. So just hang on a little bit. By the time we derive Bernoulli's equation, we'll be able to understand the exact relation. Okay, Tanish, I'm just skipping up for a moment. What is the basic idea of Bernoulli's equation? It is the relationship between these three things. Now, how we'll develop that relationship, that's coming up below. So this is the first thing that we'll do. We'll apply work energy theorem to a section of fluid like this, as it is moving in that small time dt. Now, between time t and t plus dt, as it's making that small displacement, how we can consider the net work done equal to the change in its sorry, mechanical energy. Okay, so now let's look at this closely, how we will apply this work energy theorem concept. So this is how the volume of or the volume element of fluid or the section of the fluid is looking at T equal to T. Okay. And this is experiencing a force from this side, which we had written as F2, which was pressure at that section into cross-sectional area. This section was experiencing a force due to pressure, which we had written as F1, as P1 into A1. Now, a short time later, this whole thing has moved here. So this section's displacement would have become how much? V1 into dt. Sorry, we'll write this as ds2 because it's v2 into dt. Because remember, this is moving with speed v1, and sorry, this is moving with speed v2, and this section is moving with speed v1. So the point of application of this force F1 has moved by some displacement ds1, which is v1 dt, and the point of application of this force F2 has moved in the opposite direction, but with a magnitude of how much v2 into dt. So when we write the work energy theorem, the net work done by external forces in time dt. But of course, which external forces? F1 and F2. There are no other external forces which are doing work. So that net work done is F1 ds1 minus F2 ds2. Okay. Work, as you know, is the dot product of force and displacement, but here the force is opposite to displacement. Okay. Whereas here the force is in the same direction as displacement. So F1 is doing a positive work, F2 is doing a negative work. Now further, F1 is P1 A1 and F2 is P2 A2. So this can be further reduced to P1 A1 into V1 dt minus P2 A2, which is the force, into V2 dt, which is the displacement. Okay. So now if you notice, if we incorporate continuity equation in this, okay, A1 V1 is equal to A2 V2, which is in fact the volume flow rate dV by dt. Okay. So we can write the net work done as this pressure difference P1 minus P2 into dV. So this term, A1 into V1 into dt, and this term A2 into V2 into dt, they are actually the same thing. There's the small volume dV, which is flowing through the pipe at any cross section in time dt. Okay, so this is the volume flowing through any cross section in time dt. That is the term dV. Okay, so now I've got the work done directly in terms of pressure difference, P1 minus P2. So one part of the equation, the left-hand side of the equation, I've got in terms of the pressure difference between these 2 points, P1 and P2. Now, similarly, I'll get each of the other 2 terms, the change in kinetic energy and the change in gravitational potential energy, in terms of V1, V2, that is the speed of flow, small v1 and small v2, and in terms of h1 and h2, that is the height of these 2 sections with respect to the common reference level. So just note down this part first.
Sir,
Yes.
sir, we are writing this equation by taking into consideration that the fluid that's flowing through the cross-sectional pipe is an ideal fluid. What if it was a
Yes.
real fluid? What would the equations be, and how would they?
So see, in a
change?
real fluid, now what will happen is that first of all, a continuity equation will have to be modified with something which is more like a simulation equation. Like I was telling you last
Sir, and
time.
there would be friction also, right, on the
And there
by
would
the
be
walls.
viscous force also.
Yeah.
Yes. So the
So
equivalent of drag force.
in this, we are not considering the viscous force or anything.
Yeah, because we are dealing with an ideal fluid. No? It's non-viscous in nature. Okay. So in a real fluids case, not only there will be viscosity, so that adds to this equation, but a typical real fluid will also be it will be compressible. So the density will not be uniform. So continuity equation will also not be valid. And add to that, there can be some turbulence also, turbulence and rotational motion. So it becomes highly unpredictable. So there are no ways that in which we can directly relate these 2 things by equations. And that is where the whole thing of computational fluid mechanics comes in the case of real fluids. Now, we cannot actually describe the motion of real fluids by simple equations. It has to be described by computer simulations of experimentation.
Okay.
So that's a whole different subject called computational fluid dynamics, which is like, a huge part of mechanical engineering and also aerospace engineering and aeronautical engineering, etc.
Okay. Yeah.
And
Understood.
if you do engineering in things like industrial design or manufacturing, etc., you'll go through some courses in computational fluid dynamics where you learn how those simulations are done using software models. Okay, because the system is much more complex.
Okay. Yeah. Understood, sir.
You might have seen videos and all of wind tunnel experiments and all in car design.
Yeah. Yes.
That is also like that is part of the simulation models
That's a
of
part.
CFD.
Okay.
Yes, aerodynamics of cars or vehicles or aircraft and all that. So in that, CFD plays a very huge role actually.
Okay. Yes.
Yes, home I'll scroll up, but people, are you clear with this first term of the work energy equation? How we have got the work done in time dt as that pressure difference into that small volume which is flowing. So this is a pretty standard derivation. Actually, it's nothing complicated because it's a scalar equation of work energy theorem we are applying. Okay. So you can also refer to any standard text like H.C. Verma or even better Resnick Halliday, even NCRT for the same steps of the derivation that I'm doing over here. More important is you understand the steps logically. Okay. So Soham, this is done now. Okay. Now let's come to the second term, the change in kinetic energy. Now we've got the first term work done, that is this. Now let's come to the second term, the change in kinetic energy. Now this is where the whole concept of that steady flow becomes very important, that at any cross section, all particles have the same velocity and that remains constant with respect to time. So if I look at a comparison of this initially at t equal to t, okay, and then I kind of superimpose the picture at a bit of time later, t plus dt. Okay. So there is like between the two diagrams, there is a common volume of liquid which is here, but there is add to that a certain section of liquid which is here. So let's say this section is of mass dm1, and in the second diagram there is a certain section of liquid here which is of mass dm2. Okay. So it is like at time t, the entire liquid consisted of, I'm breaking it up into a small, okay, plus this common part of mass which is, let's say, m, and at t plus dt this is transformed in shape to this, which is the same common part of mass m, but with an added mass dm2 here. Okay. Now all the molecules or all the fluid particles which are in this section here where dm2 is located are moving with a speed v2, and all the molecules or particles which are here in this section are moving with speed v1. So we can say that at t equal to t, the initial kinetic energy is the kinetic energy of the common part m plus the kinetic energy of the part dm1, and at t plus dt, the so-called final kinetic energy is again the kinetic energy of the common part m plus the kinetic energy of that lower part dm2. Okay. Now one thing you have to understand, that this common part, the molecules that are located there or the fluid particles which are located there, they have shifted, but they've shifted in such a way that at any point there was some particle earlier here. Now in this diagram, that particle has moved forward and some other particle has come and occupied its place, but it will have the same kinetic energy as this one because they are having that set type of motion, where they are following each other in an ordered way, where at every cross section the velocity is uniform. So all the particles at this cross section are having a certain velocity. In this diagram also, at the same equivalent position, all particles are having the same velocity. All the particles at this cross section are having the same velocity. So in the second diagram, now at a different time, all the particles there will have the same velocity as the previous particles. So the kinetic energy of this section is not going to change as time changes. The particles occupying that section is constantly shifting, but whichever particles are occupying that space, which is this mass m, they will have the same equivalent amount of kinetic energy. So that's why these two are the same. That is where the ordered nature of the steady flow becomes important. So the change in kinetic energy final minus initial. Because it's a small time, so we'll write that change instead of as a delta, we'll write it as a d. So this change will be equal to the kinetic energy of that section of mass dm2 minus the kinetic energy of this section of mass dm1. So that is half dm2 v2 square minus half dm1 v1 square, because it's a very thin layer of molecules. Okay. So now this thickness is, remember, ds2, which we had written as v2 dt, and this thickness, remember, we had written earlier as ds1, which was v1 dt. Okay. And this cross-sectional area was a1, and this cross-sectional area was a2. So now I can see that in this equation, now what is dm2 and dm1? It is the mass of that small section. So here dm2 is density into volume of that section, which is a2 v2 dt, which is basically rho into dv, because we've already seen that a2 v2 is equal to a1 v1, which is equal to dv by. And similarly, dm1 is rho into a1 v1 dt, that is the volume of that section, is again rho into dv. So actually these two terms are same. So you can see that dm1 is equal to dm2, which is rho into dv. That is density of the liquid into that small fraction of volume that is passing through every section of the pipe in time dt. So in other words, is a small amount of mass of liquid that is crossing any section of the pipe in time dt. Okay, so collectively this thing rho into dv, this is the mass of fluid. This whole thing, it is the mass of fluid flowing through in time dt through any cross section of the pipe anywhere. A into v into dt multiplied by rho. Okay, so we can convert a volume rate, of flow can be converted into a mass rate of flow by just multiplying by density, because dm is equal to rho dv. So this is the rate of flow of mass. This thing, okay. So when we incorporate that in this equation now, you can see that the change in kinetic energy can be written as half into, now dm2 is the same thing as dm1, which is rho dv. So take that common, rho dv into v2 square minus v1 square. So as I was telling you, each of the terms will come in terms of the individual parameters. The work done term had come in terms of the pressure difference. The change in kinetic energy term is coming in terms of some relation of v2 and v1. And as it turns out, that relationship is the difference of v2 square and v1 square. And like that, we'll see the third term, the potential energy term, will come in terms of height difference. So when we relate the three terms in the work energy equation, we'll get a relationship between v square, pressure P, and height h. Okay, so just note down this term next. So this is the second part of the derivation where we are looking at the change in kinetic energy, dk, okay, of the section of fluid which we had earlier marked as mn in time dt. That is from t equal to t plus dt. So this section of fluid, as it is moving in time dt, how much is its change in kinetic energy? It turns out its change in kinetic energy is directly proportional to v2 square minus v1 square.
So you've written dk is equal to ke dm2 minus dk dm1.
Ranak, can you speak a little louder, please? But I can't hear you.
So I'll write it in chat.
Yes, Ranak, you have some doubt? Okay, so now let's similarly look at the change in gravitational potential energy. So for that, let's make use of this diagram. I already have the horizontal reference level drawn over here. Let's remove these unnecessary things. Right, so if this was our horizontal level, which is our reference level, you can say. So with respect to this reference horizontal level, let's say the average height of fluid elements at that cross section is H2, and the average height of the fluid elements at this cross section is H1. So now you'll again understand that it's a matter of comparing this diagram, and in this comparison, dividing this into the common mass M and this mass dm1. So let's say the common part of mass is M. Now comparing it with how this has changed in time dt. Okay, this entire volume of fluid has now moved on to this position. So now it has that common mass M, but plus additionally this mass dm2. Okay, and with respect to my reference level, this mass dm2 is at a height h2. This is at a height h1. So it's quite easy to understand that at t equal to t, which is where it's here, whereas at t plus dt it has shifted like this. Okay. So at t equal to t, we can write the initial gravitational potential energy as the potential energy of the common part M plus the potential energy of that small part dm1. Okay, whereas at t plus dt, we can write the final potential energy as again the potential energy of the common part, but now plus the potential energy of the lower part dm2. So the difference in potential energy between these two instants will be a differential quantity, and that will be the difference of this, because the common part has the same potential energy. So it is the potential energy of this small section dm2 below this one here minus the potential energy of this small section here, which is dm1. So basically the change in potential energy is dm2gh2 minus dm1gh1, because we have referenced both the masses to the same horizontal level, okay, as heights as if they are having heights h1 and h2. So with respect to the common horizontal plane or common reference plane, they are having heights h1 and h2. So their gravitational potential energy change can be compared like this. Okay. Now again recall that dm1 is equal to dm2, which is basically equal to rho dv. Okay, because we have that relation that dm1 is equal to density into a1 v1 dt, and dm2 is equal to density into a2 v2 dt, and dv by dt is basically a1 v1 or a2 v2. So from all this we have this. Okay, so substituting that in the equation further, we get the relation that the change in potential energy is rho dv into g into h2 minus h1. So as expected, the change in potential energy, the third term, is proportional to the height difference h2 minus h1 at these 2 points. So comparing the three things, pressure, the kinetic energy term, and the potential energy term, we are getting a relationship between pressure on its own, or pressure difference for the work done side, v2 square minus v1 square for the kinetic energy term, and h2 minus h1 for the potential energy term. So when we put these three terms, when we plug them into our work energy equation, we will see that we'll get a relationship between pressure, square of v, and h compared at any 2 points within the flow. So So just like continuity equation gave us a relation between area of cross section and velocity of flow at any 2 points, Bernoulli's equation will give us a relation between pressure, speed V and height h. Or in fact, it will be actually in the form of pressure square of speed V square and height h compared for any 2 points within the fluid in motion, in streamline motion. So through this, you can also understand how diverse the application of Newtonian mechanics is across physics. It's not just applicable to a particle in motion or a block in motion under the action of friction, gravitational force, inclined plane, pulley systems, tension, and things like that, normal reaction and things like that. It can also be applied to a system which is what we call a continuous mass system. That is a continuation of mass distributed over the volume of a fluid while it is in motion. Application of Newtonian mechanics to a system of particles which, for example, might even have variable mass, like the rocket system you would have studied about, okay, or between rigid bodies that are interacting with each other through collisions, in collisions. But the basis, the fundamentals for analysis of all these kind of systems is nothing but Newton's laws itself, okay, and then the application of Newton's laws into things like work energy theorem, conservative, non-conservative forces, potential energy, kinetic energy, the relationship between these and work done. So these are the basic building blocks of mechanics. It is applied across diverse spectrum of physics. That spectrum extends well into engineering also, not just your 10+2 or high school level physics. Okay, so there appears to be a correction in the previous one. I'll just check. Ranak has pointed out that in kinetic, yeah, so final minus initial, it is kinetic energy of dm2 minus kinetic energy of dm1. So Ranak, what seems to be the problem? Oh, no, see, this what I've written is correct only because see, at time t plus dt, the section of fluid consists of, yeah, here, at time t plus dt, the section of fluid consists of the mass, common mass m plus dm2. No? So this is the final one, no? And the above one is the initial one. So it is final minus initial. No? So it's like to this middle section, you've added the mass dm2 in the final diagram. Okay. Whereas in the first diagram, you had added the mass dm1. So the kinetic energy initially was the middle parts plus dm1s. And after a time dt, it became the middle parts kinetic energy is this section over here, dm2, minus the kinetic energy of this section, dm1. That's why it's coming in this order. It's 2 minus 1.
Okay,
Hope that is
sir.
clear, Anna?
Sir.
Okay. Now, similarly, hope this term is also clear. So again, it's coming in same order. You can see the suffix 2 minus the suffix 1, because the final state is the middle mass plus dm2, whereas the initial state is the middle mass plus dm1. So the change in potential energy is the potential energy of this part, the green shaded part dm2, minus the potential energy of this part, the red shaded one, which is dm1. So that's why again we have that in order h2 minus h1. Now let's put these together in our work energy relation. So finally, going back to the work energy relation, or if we write it in delta form, we'll say that work done is equal to change in kinetic energy plus change in potential energy, like this. Okay, but here we have written this as P1 minus P2 into that differential volume dV, where that differential volume is A1 B1 equal to A2 V2. So dV by dt is equal to A1 B1. So dV is equal to that's this. So this was equal to now half rho dV into V2 square minus V1 square. And this was equal to rho dV into G into H2 minus H1. So if you like, you can write an intermediate step also here. This is half dm2 V2 square minus half dm1 V1 square. This is dm2 GH2 minus dm1 GH1. But you can understand again that dm2 is equal to dm1 is equal to rho dV. So now cancelling off the dV on both sides, or if we write this in delta form, we'll write it as P1 minus P2 into delta V, that is the volume which has flowed in time delta T, is equal to half rho delta V. So similar kind of expression, no difference at all. But only D is replaced with delta. So cancelling off the dV or the delta V, whatever, we have the relation that P1 minus P2 is equal to half rho into V2 square minus V1 square plus rho G into H2 minus H1. Now if we organize this equation in such a way that we are comparing all the parameters at the point 1 on the left hand side and at the point 2 on the right hand side. So bring all the terms with subscript 1 on the left hand side of the equation. So we have P1 plus half rho V1 square plus rho G H1 becomes equal to on the right hand side all the terms having subscript 2. So P2 plus half rho V2 square plus rho GH. So this becomes one way of expressing Bernoulli's equation. That if I compare any 2 points in a fluid, inside a fluid which is in steady flow, then the sum of these 3 terms will be equal for those 2 points. So this is the comparison of pressure V square and H for any 2 points, let's say 1 and 2, which are arbitrarily selected. That means we can select them freely without any boundation. That is again ideal fluid in steady flow. Okay. And if you also notice that each of these terms has the same dimensions, the dimension of pressure or the unit of pressure in any system will be equal to the unit of half rho V square, or that is the same as the unit of rho V square, will be the unit of rho GH. And that is actually equal to the unit of energy divided by the unit of volume, or the unit of work done divided by volume. So it's like a work energy relation, but instead of relating energy and work done, we are relating like energy per unit volume with work done per unit volume kind of term. So if you think of this P1 minus P2 term here, it's like the work done per unit volume. If you look at the half rho V squared reference term. It's like similarly rho g h2 minus h1. So they are like energy per unit volume terms. And also we can generalize this equation and say that in general for any 2 points, or rather in general at any point, the sum of these 3 quantities, pressure, kinetic energy per unit volume, and gravitational potential energy per unit volume with respect to some reference level, that will be the sum of these 3 will be a constant. This is another way of expressing the same thing, and this is called Bernoulli's equation. Whether we express it like this by comparing any 2 arbitrary points, or we generalize it, we say this is the statement of Bernoulli's equation. Okay, so that's all there is as far as equations of steady flow of an ideal fluid is concerned. Continuity equation on the one hand and Bernoulli's equation on the other hand. Continuity equation is actually like a statement of conservation of volume, or conservation of you can say the incompressibility of the fluid, that is the density remains constant. And Bernoulli's equation is like an application of work energy theorem to fluid mechanics. So next lecture, I think day after or whenever we have this week, Friday, I think we will pick up the applications of Bernoulli's equation, and we should be in a position to discuss questions from H.C. Verma and the module very soon, probably in the next lecture itself. And we will do like questions from both the sections together now. Hydrostatics, if there are any doubts pending, that along with hydrodynamics questions, we'll pick that up starting from the next lecture itself, after looking at some of the standard applications of Bernoulli's equation. So that's it for today's session, people. Wish you all the best. Thanks for attending.
Sir, can you minimize it once?
Yes.
Sir,
Yes. Yes.
sir, please send the PDFs of this lecture.
Yes, I'll send the
Yes,
PDF.
sir, please, sir.
Yes. Yes, Samar. So the theory part of the chapter more or less is complete. We will see the application of this in certain standard type of problems next time. But as far as the
Okay,
theory
sir.
derivation and the formula is concerned, that is complete, right?
Thank you,
Yes,
sir.
sir.
Okay. Okay, people. Wish you all the best.
Thank you, sir. Bye, sir.
Bye, people.
Thank you, sir.
Thank you, sir. Bye.
Okay. Bye, people. Bye.